Welcome to Maclaurin and Taylor series. This video is on Maclaurin series, and the rather handsome chap that we've got here is Colin Maclaurin. The theory behind this is that we can take any function f of x and we can find an approximation to that function using a polynomial. So our general polynomial is just going to be a constant plus a constant times x plus a constant times x squared plus a constant times x cubed, and so on. Now what Colin Maclaurin realised was that we could then evaluate this at 0, and any term in our polynomial that had an x in it would obviously be nullified, and I'd be left with a naught. Next we realised that when we differentiate our function, this constant is going to disappear, and what I'm left with is a1, 2a2x, 3a 3x squared, and so on. And again, evaluating this derivative at 0 would give me a1, and all of these terms would be nullified. We can continue in this way, differentiating for the second time to give me and so on, repeating the process. And so on. Now, what we have to realise at this point is that obviously for the rest of our polynomial we're going to get these decreasing multiplications, 4 times 3 times 2 times 1, and above is going to be 5 times 4 times 3 times 2 times 1, and what we need to realise is obviously that we can write this using factorial notation as 4 factorial. So what I really have here is 3 factorial. This I can express as 2 factorial, 2 times 1, and so on. So I now have a nice way that I can write down my original function, because I know that a0 is just the function evaluated at 0. I know that a1 comes from the function derived and evaluated at 0. Now here I'm going to have to divide through by 2, or by 2 factorial, to give me my value for a2, which is going to be f double prime evaluated at 0 divided by 2 factorial. a3 is now going to be f triple prime evaluated at 0 divided by 3 factorial, and so on down the line, and we get this nice pattern where the number that we are dividing by, the factorial that we're dividing by, is equal to the number of derivatives that we have taken, which takes us to this formula here. Now you'll see that in higher powers we've just put this in brackets to indicate that we're differentiating f r times. So let's have a look at how this can be applied. Let's try and find a Maclaurin series expansion for cosine of x. So first of all, let's remember the formula. This is always something that's going to be given to me, so I may as well just start using it. Now what I'm really interested in is my function f of x, so I want to find f of x, which currently is equal to cosine of x. Now all I need to be able to do is to derive this function and evaluate it at 0, so down the side of my page here I'm going to start doing that. Now I just evaluate these functions at 0, and f of 0, well, cosine of 0 is 1, f prime of 0, sine of 0 is 0. So cosine of 0 is 1, and we've got minus that, which gives me minus 1. And there we have it. Now I have my coefficients, I can simply write my function. So I know that f of x will be equal to f0, which was 1, plus x times by f prime. Now this evaluated to 0, so this term will be 0. My x squared term is preceded by f double prime. Now f double prime is minus 1. So I end up here with minus x squared over 2 factorial. Likewise, my cubic term will be 0, and I'll be left with my quartic term, which is 1 lot of x to the power of 4 over 4 factorial. X to the power of 5 will be 0 again, because my coefficient here will be 0, and minus x to the power of 6 over 6 factorial, and so on. And we can see that cosine has a nice regularity about it. Let's just tidy this up and get rid of our addition sign. And there we have it. What you might like to do now is to pause the video and to have a go at trying to find power series expansions for the following functions: the exponential, the natural logarithm of 1 plus x, and sine of x. If you simply can't wait, here's the next page. So these are all things that are given to us in the formula booklet. So notice here was our cosine that we found. Hopefully you've gone away and you found out your exponential, you found out log of x, you found out sine of x. Let's now look at how these things can be used for composite functions. So composite functions where I'm finding a function of a function. So what I'm interested in doing here is to write down the first 3 non-zero terms in the series expansion in ascending powers of x of this function. Now, I know the power series expansion of sine. It's something that I'm allowed to quote. It's in the formula booklet, and it's also just here. Armed with this knowledge, all I now need to do is to substitute my x term here for 3x squared. So every time I see an x, I'm going to write down 3x squared. Every time I see an x, I'm going to write down 3x squared. So my sine function of 3x squared becomes 3x squared minus 3x squared cubed over 3 factorial plus 3x to the power of squared all to the power of 5 over 5 factorial. I'm stopping at this point because I'm only asked to write down the first 3 non-zero terms. Okay, so let's now go through and tidy this up. So this is going to be 3x squared minus, expanding the indice over the bracket, I get 27x to the power of 6 over 3 factorial, which is 6, plus 3 to the power of 5 is 243, x to the power of 10 over 5 factorial, which is, I believe, 120. At this stage I'm just left with a nice simple simplify, so I recognise that I've got a common factor of 3 here, so I can write this as 9x to the power of 6 1 over 2, and again I've got a common factor of 3 in my numerator and denominator, so this becomes 81x to the power of 10 all over 40. And there we have it. Okay, so for our next example we're looking to do something similar. So first of all, let's remember what the power series expansion of the natural logarithm is. Now, I'm not quite in a position to be able to use this straight away because I need log of 1 plus x. So I need to take my logarithm and use my logarithm laws to try and rewrite this in terms of 1 plus x. So remember, divisions here can be rewritten as subtractions, so this becomes the logarithm of 1 minus x minus the logarithm of the square root of 1 plus x. And again, log laws here will tell me that I can rewrite this as log of 1 plus minus x minus a half of log of 1 plus x. This is much nicer. This is now in the exact form that I want to be able to use because I've got 1 plus a function of x. That just means that in my power series expansion, wherever I see my x, I can replace with my new functions. Okay, so being sure to be neat about how I'm working, and remembering that I only want to write down the first 3 non-zero terms, log of 1 plus x can be written as x. Sorry, what am I doing here? We've got 1 plus minus x as our function, so this is the thing that I was saying that we need to be careful about. Let's just quickly scooch back to the point where I can put in minus x minus x squared over 2 plus minus x cubed over 3. That deals with my first. So here we've now got here. Now let's deal with the second. That's going to be minus a half of. Now this is just a regular expansion, so that becomes x minus x squared over 2 plus x cubed over 3. And this corresponds to this. Finally, moving to collect like terms, I have minus x over 2 for my second bracket. Then I've got minus x squared, which is x squared over 2, and then a half of minus x squared. And remembering now that I need to multiply these negatives, so negative times negative is going to give me plus x squared over 4, a half times a half, and finally negative x cubed, which is going to give me negative x cubed over 3, and negative times positive gives me negative x cubed over 6. Okay. Minus x minus another half of x is going to give me minus 3x all over 2. Minus x squared over 2 plus a quarter of x gives me just minus a quarter of x squared. And finally, minus a third of x minus a sixth of x. Well, this is really 2/6 of x. And if I take away another sixth, it gives me minus 3/6. And 3/6 is the same as 1/2, so this becomes minus x cubed over 2. And on we go. Okay, so this is one of our more complicated examples. In this case we want to find the series expansion for e to the power of sine x, up to and including terms in x cubed. Now, let's just write out first of all the power series expansion for e to the x. Okay, again we can get this from our formula page. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Now I only want terms up to and including x cubed, so I know I can stop at this point. Okay, now let's think about sine. Now, sine of x is x minus x cubed over 3 factorial. And again, I can stop at this point because I only want terms up to and including x cubed. Now, all I need to do is take my sine function and place it in everywhere I see an x in my exponential function. And I end up with e to the sine x being approximated by, because I'm going to leave out a few terms here, so 1 plus x minus x cubed over 3 factorial plus x minus x cubed over 3 factorial squared all over 2 factorial plus x minus x cubed over 3 factorial all cubed over 3 factorial, which becomes 1 plus x minus x cubed over 3 factorial. Now, when I expand this bracket, what I'm going to end up with is a term in x squared, x times x, it's going to give me a term in x squared. I'm going to end up with a product term in x times by x cubed, which is going to be an x to the power of 4, and I'm going to end up with another term in x to the power of 6. Now remember that I only want up to and including x to the power of 3, so I do not need either of these terms. The only term that I'm interested in is the one that's going to come from multiplying x by x, which is going to give me x squared over 2 factorial. Finally, looking in a similar way at my final bracket, if I'm cubing this expression, it means that I'm going to end up with something involving x cubed, then something involving x times x cubed, x times x cubed, which gives me x to the power of 5, something that involves x times x cubed times x cubed, which gives me something involving x to the power of 7, and finally something in x cubed times x cubed times x cubed, which is x to the power of 9. And again, I don't want any of these. The only one I'm interested in is that first one. So that is going to become plus x cubed over 3 factorial. Looking to simplify now, I can see that my x cubed terms are going to cancel out, and I'm left with 1 plus x squared over 2 factorial. Here's my approximation. Okay, thanks very much for watching. The next video is going to be on Taylor series.